Hello students, welcome back to my YouTube channel Physics Club by Shakti sir. So in today's lecture we will discuss about the inelastic collision, particularly head-on inelastic collision, that is the inelastic collision in one dimension. Head-on and one dimension both have the same meaning. In this lecture we will also discuss three very important numericals which is based on the inelastic collision. Few are simple and one is the more complicated. So let's discuss the fundamentals first, how to tackle the situations, and then we will discuss the numericals based on that. Again, collision. Collision means it is totally based on the conservation of linear momentum. So let's start with the theory part. So it is based on the conservation conservation of linear momentum. Linear momentum. So actually, what the inelastic collision is, inelastic collision takes place when the two objects collide with each other and their kinetic energy is not conserved during that collision. It means that the total kinetic energy before the collision and the total kinetic energy after the collision are not equal, because the kinetic energies are equal when it's elastic collision. So in elastic collision, in this situation of collision, the body gets some form of deformation. That is, during the collision, when the two bodies collide with each other, some of the energy get lost or wasted in the form of thermal energy, in the form of rotational energy, in the form of deformation potential energy, in the form of sound energy, right? So all these energies will not come back after the collision take place. So in this situation, only the conservation of linear momentum concept will be applicable, and that concept is applicable when we consider the system is isolated. So we are considering system is isolated. That is, no external forces acting on this system. Only under these situations, the two bodies having masses m1 and m2 are conserved. So let's say it has a mass of m1 and it has a mass of m2. They are initially moving with u1 speed and it is moving with u2 speed. So the initial linear momentum will be equal to the final linear momentum, right? So this is the very important thing we need to discuss. So what we can write, and after the situation, so let's say this is the before situation. So this is before the collision, and after the collision, again we can say the masses, again we can say the situation that masses m1 and m2 are moving some v1 velocity and v2 velocity, right? If you know the concept, you can skip this part and directly go to the numerical part. So now the situation will be m1 v1 vector plus m2 v2 vector. So the only equation we will use, as we discussed also in the earlier lecture, that is collision in elastic collision in one dimension. That is, so the equation we can equate here, the linear momentum before the collision is equals to linear momentum after the collision. So this is the situation after the, so before the collision you can write m1 u1 vector plus m2 u2 vector is equals to, after the collision we can write m1 v1 vector plus m2 v2 vector. So this is the situation, this is the equation we will use to solve the numericals. Okay, this is very perfect. uh, Other than this, as the conservation of kinetic energy is not valid here, but the conservation of energy, that is, the conservation of energy is valid here also. Sometimes we will use the concept of conservation of mechanical energy, right? It depends on the question to question. So this is the inelastic collision. So mostly in inelastic collision, what will happen? The two bodies after the collision separate from each other. But there is a situation when the two bodies after the collision stick together with each other. So that part is called particularly the perfectly inelastic collision. So what we called perfectly inelastic collision. So in perfectly inelastic collision, what the situation? The two bodies stick with each other. The two colliding bodies stick with each other. Stick with each other. That is, the situation can be like this, as initial situation. This is the initial situation. The two bodies are moving with some different velocities u1 and u2 with masses m1 and m2, and after the situation they stick together. That is, they behave as a one body. When they behave as a single body, okay, when they behave as a single body, then what will happen? Their combined mass will be m1 plus m2, and this entire body is moving with some common velocity vc. So in this situation, we can write the conservation of linear momentum like this: m1 u1 vector plus m2 u2 vector is equals to m1 plus m2 and v common. So this equation is used in these situations. Again, I am repeating that in these situations, the conservation of kinetic energy concept is not valid. Conservation of kinetic energy is not applicable, but we can apply the conservation of mechanical energy. We can apply conservation of mechanical energy. All right. So this is the very small part of the situation. So because in collision, if someone asks you, do you know the collision? But you need to remember conservation of linear momentum, conservation of mechanical energy. Rest is just the practice of the numerical, different type of numericals. Okay, there is one more term, that is the coefficient of restitution. We will discuss the coefficient of restitution in the next video. But here we will just apply the concept how to solve the numericals. So our first question is, so here you can see a neutron having a mass of, this is the mass of the neutron, is moving at a speed of 10 raised to power 8 meter per second, collide with a neutron at rest and stick to it. So stick to it. After the collision, they both combine with each other. Mass of the neutron is also given. So calculate the speed of the combination. Straightforward question. Let's try to solve it. So initially, only the neutron is moving. So the momentum of the neutron, so mass of the neutron and the speed of the neutron is the momentum initially. And after, when they combine with each other, this is the mass of the neutron and mass of the neutron combined with some common velocity vc. Let's put the value. Once you put the value, you come to know that the mass part is 1.67 into 10 raised to power minus 27 kg, and the speed is given 10 raised to power 8 meter per second, and the combined mass is, you can see 10 raised to power minus 27 is common, and it is 1.67 plus 3.34, and the velocity is vc. Because we don't know the speed, we will calculate it. So we can easily cancel these terms. 10 raised to power negative 27, we can easily cancel these terms. So the next step is 1.67 into 10 raised to power 8 is equals to, so once you add these, you will get 5.01 and multiply Vc. So in simple calculations, 1.67 divided by 5.01 into 10 raised to power 8 is nothing but Vc. So our final answer will be 0.33 into 10 raised to power 8 meter per second is equal to the common velocity. So this is our final answer of this numerical. Okay, answer. So this is the easiest part. What we do, we just apply the conservation of linear momentum. This is the initial linear momentum of the system, and this is the final linear momentum when the two particles stick with each other, right? Let's move to the question number second. A 6 kg sled is moving on a frictionless ice at a speed of 9 meter per second. Okay, so let's draw the sledge. So let's consider we have a sledge like this, and its mass is 6 kg. So mass of the sledge is 6 kg is given, and it is moving, initially it is moving 9 meter per second. This is the initial situation. So we can easily write the initial linear momentum, that is mass of the sledge multiply the speed of the sledge. And after, so what's happened after? The sledge is moving with some speed v, but there is a, you can see when a 12, it is clearly written, when a 12 kg package is dropped into it from above. So if 12 kg package is dropped, so into it a 12 kg packet, this one. So let's say this is a 12 kg packet, right? Mass of the packet, or uh, mass of the packet, right? This one. What is the new speed of the sledge? So we will apply the conservation of linear momentum. So initial linear momentum is equal to final linear momentum. The initially it is mass of the sledge multiply speed multiply u, that is the speed of the sledge, and after some time you will get, when they are moving together, the box and the sledge. So mass of the sledge plus mass of the packet whole multiply speed. Let's put the values. When you put the values, what you will get? You will get mass of the sledge, which is 6, and the speed is 9, is equals to again 6 plus 12 and v. Okay, so 6 multiply 54 is equals to 18 and v, right? Then you can calculate 54 divided by 18 equals to v, and it is nothing but 3 meter per second. So this is the velocity with which the combined system is moving. So this is our answer. So this is our answer. Okay. Question number 3. Let's discuss question number 3. What the question number 3 is saying? Question number 3 is saying two particles having twice the mass of the other. Okay. So first line is very important. Having twice the mass. So solution. What does it mean? Having twice the mass. That is, if m1 equals to m, then m2 equals to 2m. This is the meaning of this line. Are held together with a compressed spring. So there is a compressed spring like this, and there are two blocks attached with it. One is m1 and one is m2, compressed. The energy stored in the spring is 60 joule. Okay, so initially it is compressed, and the only energy, because the two blocks are at rest, so there is no kinetic energy associated with these blocks. The only energy initially is 60 joule, which is stored in the spring. So how much kinetic energy does each particle have after the two are released? So when we release, when the spring is expand, when the spring uh, free from the restrictions, so this block will move in this direction and the m1 will move toward the left side, then both will get the kinetic energy, and there is no elastic potential energy stored in the spring in the final process. Okay, so we can easily equate the conservation of mechanical energy equation and one from the linear momentum, conservation of linear momentum. So from the situation of conservation of linear momentum, clearly we can write that the initial momentum, as both the block at rest, so initially both blocks are at rest. So it means the initial momentum is equals to 0. Initial linear momentum is equal to 0. But finally, what is the final situation? Finally, the linear momentum P final after can be written as this will move in this direction, it will move in this direction. So what you get? Let's say this is u1 and let's say this is u2. So it is m1 u1 vector plus m2 u2 vector. So based on the so conservation of linear momentum, conservation of momentum. So once you apply the conservation of momentum, what you will see, you will get the situation like initial momentum is equal to 0 and the final momentum is equal to m1 u1 vector plus m2 u2 vector. Okay, so from the you will get m1 u1 vector is equals to negative of m2 u2 vector, like this. Put the value m1 is equal to m, this is negative, this is positive. Okay, so m1 is equal to m and u1 equals to m2 is equal to 2 times of m and u2 vector. So mass term can cancel, so mass term and mass term can cancel, so we have the relation that is negative of u1 vector equals to 2 times of u2 vector. So this is the relation we can use somewhere in our solution. Okay, all right, let's move forward. What else we can do? We can apply the conservation of linear momentum. Oh, sorry, the conservation of mechanical energy. So conservation of mechanical energy. Mechanical energy. So we can apply the conservation of mechanical energy. You can see the initial mechanical energy is totally in the is stored in the spring. So elastic potential energy, elastic potential energy. This is the initial, and finally both the blocks are moving. So the kinetic energy of both the blocks is equals to kinetic energy of blocks. So we will write the value. So the value is, this is half, oh sorry, it is given, it is 60 joule, and the kinetic energy of both the blocks is 1 by 2 m1, which is equals to m, and u1 square plus 1 by 2 m2, which is equals to 2m, and u2 square. Let's put the value of u1. So 60 equals to 1 by 2 m. So you just get u1 is equal to negative of 2 time of u2 square plus 1 by 2 2m u2 square, right? So this is what we get here. u1 is equal to negative of 2u2. All right, let's solve this one. So it is 60 is equals to m by 2 multiply 4 u2 square plus half 2 times of m u2 square. So it is 60 is equals to, let's take some common value, 1 by 2. We can take mass also common, 2m u2 square. If we take this one common, you will get here 2 plus 1, 2 plus 1. Okay, so 60 divided by 3 equals to 1 by 2, and mass 2m is the mass of the second, u2 square. So what is this? This is the kinetic energy associated with the heavier body, so which is equals to 20 joule equals to kinetic energy of m2, that is the heavier object. So what is the kinetic energy of the lighter object or of mass m1? So kinetic energy associated with lighter mass is, how you get 60 minus 20 joule, which is equal to 40 joule. This is our required answer. Okay, so lighter have 40 joule of kinetic energy and the heavier mass have 20 joule of kinetic energy. So this is all about today's lecture, the three numericals and very few concepts. If you like this situation, if you like this video, please subscribe my channel and share it with your friends. Wish you all the best. Bye bye.